This is the second pre-recorded lecture from Chapter 9, and whereas the first pre-recorded lecture focused in on the energetics primarily of ionic bonding and lattice energy, this lecture will focus on the energetics of covalent bonding. You may remember from the first lecture that I drew Bohr models to demonstrate ionic bonding. So this is kind of an abbreviated form, and I showed that the valence electrons are the ones involved in chemical bonding, that ionic bonding involves a complete transfer of an electron from the metal to the nonmetal, and that what you end up with is a cation and an anion that are electrostatically attracted to one another. Covalent bonding, on the other hand, shares electrons. It still involves the valence electrons, as all chemical bonds do, but instead of the valence electrons being transferred, they are shared. They're held in between two atoms. There's still an electrostatic attraction, but it's between the electrons in one atom and the protons in the nucleus of another one. As I'm sure you are probably aware, we have single covalent bonds represented by a single line. Each covalent bond has two electrons that make it up. There are also double covalent bonds, 2 electrons in each of the 2 bonds for a total of 4 electrons. And of course there are triple covalent bonds. All 3 of those bonds contain a total of 6 electrons. We talked a little bit about the distance between the atoms in an ionic compound, and so we are interested in that for covalent bonding also. The distance tells us the bond length, and of course that bond length in a covalent bond is primarily determined by the size of the atoms involved. Smaller atoms will have smaller bond lengths, and the larger the atom gets, the larger the bond length, or the farther apart they will be from each other. Now, one final important consideration is the relationship between bond length and how many bonds are in between two atoms. So single bonds have a longer bond length than double bonds. So you see how the bond length decreased when we added a second bond between the atoms? And triple bonds, of course, have the shortest bonds of all. Each bond represents a level of attraction between the two atoms. So as you increase bonds, so you increase the number of bonds, bond length decreases. Whereas with ionic compounds, we talked about lattice energy. For covalent compounds, we're going to talk about bond enthalpy. In a covalent compound, if you had tweezers small enough, you could actually tweak out or pull out one individual molecule. Obviously, we can't, they're too tiny. But each molecule exists independent of the other molecules. Not completely independent, but pretty much. In an ionic compound, it's a three-dimensional network. So even though we tend to write it like an individual unit NaCl, it really isn't a single unit. It's a three-dimensional network of cations and anions that are held very tightly together. So there's not one individual molecule, and so that's how we talk about lattice energy. So let's look at bond enthalpies or bond energies for a variety of covalent bonds and see what you would expect. The first thing that you should notice that we've already talked about is the difference between a single bond, a double bond, and a triple bond. Okay, So we talked about bond length before. Let's look at bond energy. So as the number of bonds increases, bond strength or energy also increases. Okay, you can see that here. This slide goes over another extremely important point, and that is that bond breaking, so anytime you break a bond, is endothermic. What does that mean? It means that to break a bond requires energy, just like breaking anything, right? If you wanted to smash up something, you'd get a hammer and you'd have to put energy into it to break it. Same thing with bonds. Bond making, when you make a new bond, is always exothermic. Otherwise it won't happen. So anytime two atoms decide to bond, they do so because it's energetically favorable. It's exothermic. So remember, that's really important. And here's a formula that uses that concept. If you want to find the enthalpy of an entire chemical reaction, you can do that. Here's yet about a fourth way to find enthalpy of reaction. We found it through Hess's law and all sorts of laws. Anyway, so here's another one. You can sum the bonds broken and subtract from that the sum of all the bonds formed. It sounds very simple. It's a little bit complicated because you have to look at the reactions, to look at the reactants, and you have to decide what are all the bonds that are broken. So you've got to compare the reactants to the products. Let me just give you an idea. So what bonds have been broken here? We have broken the carbon-bromine bond. Have we broken any other bonds? Nope. So that has been broken. And what bonds have we made? We have made a carbon-oxygen bond. So to calculate the enthalpy of reaction for this particular reaction, you would find the bond energy of a carbon-bromine, and you would subtract from that the bond energy of a carbon-oxygen. Let's work through another example. This takes careful paying attention and tallying up. You got to pay attention to coefficients also. So in this case, let's see, each of these little junctures represents a carbon atom. All right, so what are the bonds that we have broken here? I usually make two columns. One for bonds broken, which you look on the reactant side for, and one for bonds made. All right, what have we broken here? Let's see. We have broken the carbon triple bond carbon, and we have also broken, well, we have two of those, okay? We've also broken two carbon hydrogens, two on each molecule, but we have two molecules. 2 times 2 is 4. So we've broken a total of 4 carbon hydrogen bonds. Have we broken anything here? We certainly have. We have broken 5 oxygen double bonds. If there's a double bond, you make sure you show it as a double bond. All right, those are the bonds we've broken. Let's take a look at the bonds we've made. We have made carbon-oxygen double bonds. How many of them have we made? Well, we've made 1, 2 for each molecule, and we have 4 molecules. So 4 times 2, we've made 8 carbon-oxygen double bonds. And we have also made hydrogen-oxygen bonds, 2 of them for each water molecule, and we have 2 water molecules, so 2 times 2 is 4 hydrogen-oxygen bonds. So now you look in the table, which will be given, and you find out the bond energies for everything that's been broken and made, and you plug into the formula. And remember that what that was, that's the enthalpy of this reaction is equal to the sum of the bonds, let's shorthand this, broken, minus the sum of the bonds made. Here is a typical multiple choice question to make sure you understand the concept. Remember what I said earlier, that all bond breaking is endothermic and all bond making is exothermic. So let's see if you can pick out which of the following statements is true of an overall endothermic reaction. So if I have a reaction, let's say that looks like this, there are my reactants, and let's say it makes AD, it's a double replacement reaction, and BC. And let's say that this reaction is endothermic, so that means the enthalpy of reaction would be positive. What does that mean? Which of these do you think would hold true? So pause the video for a minute, see if you can think your way through that, and if you can, great. If not, I will explain it in a moment. Here's a hint, first of all. Here's the equation where we use bond energies to figure out enthalpy of a reaction. So if the enthalpy of a reaction is endothermic, which is what this question is asking, that means delta H reaction has a positive sign. And what combination of bonds broken and bonds made would give a positive value? That means that the energy for the bonds made must be smaller than the energy for the bonds broken. In order to get a positive value, what you're subtracting must be smaller. So let's see which one of these fits with that. Strong bonds break, okay, and weak bonds form. Does that fit in? If you have strong bonds, you're going to have a large value for the broken part. If you have weak bonds formed, that means you've got a smaller value. That fits. Yep. So B is the opposite of that. We know that's not true. Let's see if there's more than one answer. The bonds that break and those that form are of approximately equal strength. No, because if they're approximately equal, delta H reaction would be about 0. Okay? An endothermic reaction does not depend on the bond strength. Baloney. This reaction shows you that it depends on bond strength. So the correct answer is A. Now we're going to learn how to draw Lewis structures of molecules. In the last lecture, we learned how to draw Lewis structures of individual atoms and of ionic compounds. We're going to learn now covalent compounds, and they get a little bit more complex. Follow these rules very carefully, and they will never fail you. Okay, so if I were you, I'd write these rules down on a note card or someplace on a piece of paper that's easy to find later. Number 1, when trying to write a Lewis structure for a covalent molecule, first find the sum of all valence electrons. So we're going to work on examples as we go through the rules. Phosphorus is in group 5A, so it has 5 valence electrons. Chlorine is in group 7A, so each chlorine has 7 valence electrons, and there are 3 chlorines, so 3 times 7. So 5 times 21 means there are a total of 26 valence electrons in this compound. That is step 1. If the compound is an anion, okay, so if it were PCl3 with a negative charge, add 1 more electron, because that negative charge means an extra electron, that would have 27 valence. If it's a cation, you subtract an electron. So if it were PCl3 with a plus charge, there would be 25 valence electrons. The second step is arrange the atoms so that the central atom is the least electronegative. You know the trend for electronegativity. It goes like this. So fluorine is the most electronegative and cesium is the least electronegative. So put the least electronegative element in the middle. It's almost always the first element in the formula. So PCl3, it's almost always that first element they give you almost always goes in the middle. Not always, but the vast majority. Keep in mind the central atom can never be hydrogen. All right, so part of step 2 is to connect all of the atoms together using single bonds to start with. Okay, so you see I did that here. Now keep in mind off to the side someplace, how many electrons do we have to place or find homes for? How many valence electrons did we have? We had 26 electrons. How many have we placed so far? Each single bond has 2 electrons. So far we've used 6 electrons. So we need to place 20 more electrons. Okay, so let's go on to step 3. Step 3 is to give octets to the outer atoms. So you can see with these dots, I gave each of the outer atoms an octet. That's 2, 4, 6, 8. So each chlorine atom has 8 electrons. And so far, I have placed 24 electrons in this Lewis dot structure. I have to place 26, so I have 2 more electrons I need to place. So that takes us to step 4. All right, if you have electrons left over, in this case we have 2 electrons left over, place them on the central atom. So that's what I've done here. Okay. So if at this point all of the atoms have an octet, you're done. And that's the case in this point. This is the correct Lewis structure for phosphorus trichloride. There are some cases where when you finish step 4, the central atom will not have an octet, and we'll talk about what to do when that happens. So let's look at HCN. If we count valence electrons, there are 10 valence electrons that we had to place. We go through step 1 through 4, and we've used all 10. They're all used up. Then you ask yourself, do each of the atoms have a full outer shell or an octet? Well, hydrogen's happy with 2 electrons, so it's okay. Nitrogen has an octet, so it's okay. Carbon, however, with this Lewis structure only has 4 electrons. Not cool. Every atom except for hydrogen and helium wants 8 electrons. So if you find that you're in that situation and you have no more electrons to place, what you do is you take one of the non-bonding pairs on one of the terminal atoms and turn it into a double bond. So we would originally get this. So remember, we've taken away the lone pair that was on the top of nitrogen and turned it into a double bond. So now you say, okay, now does the carbon have an octet? It has 2, 4, 6. It still doesn't have an octet. So as many times as you need, take a non-bonding pair and make a multiple bond. In this case, we're going to go to a triple bond. So now we have this structure, and now you can see that carbon does in fact have 2, 4, 6, 8. Carbon has an octet now. So that is a good, stable Lewis structure for this compound. Sometimes you end up with 2 possible Lewis structures. Check this out. Carbon dioxide has 16 valence electrons. If you follow those rules, you could end up with either one of these Lewis structures, and you then have to decide which one is the better Lewis structure, which one is more stable. You use something called the formal charge to determine the stability of the Lewis structure. This sounds a little complicated to begin with, but it really is quite easy. So the formula for formal charge is the number of electrons an atom has when it's alone minus the number of electrons that same atom has in the compound. Okay, so what am I talking about? So let's look at the structures for carbon dioxide. How many valence electrons does oxygen have when it's an atom on its own? Okay, it has 6 originally. It's in group 6A. Then how many electrons does oxygen have when it's in this compound? So this is how you count. You count all lone pair electrons, so 1, 2, 3, 4, and then if it's a bond, you count half of the electrons. Half of them go to oxygen and half will go to the other atom, carbon. So it gets 1 electron from each of these bonds. So that means that oxygen in this compound has 1, 2, 3, 4, 5, 6. So in other words, the oxygen in this structure has the same number of valence electrons when it's on its own or when it's in this compound. Therefore, it has a formal charge of 6 minus 6, or 0. Formal charge of 0 is good, okay? That's what you're striving for. So if you go through the same process for the carbon atom, carbon on its own as an atom has 4 valence electrons. And in this compound, remember that you count 1 from each bond, so it has 1, 2, 3, 4. So it has 4 when it's in this compound. So carbon also has a formal charge of 0. So the bottom line is all of the atoms in this structure of carbon dioxide have a formal charge of 0, which makes this a very good Lewis dot structure, good stable Lewis dot structure. Let's look at the other possibility that you might have come up with when drawing a Lewis structure for carbon dioxide. Let's calculate the formal charge for the oxygen on the left. Oxygen always has 6 to begin with. In this particular structure, it has 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1, so there is a formal charge of minus 1. Carbon has a formal charge of 0, which is good. The oxygen on the right has a, let's see, how many electrons does it have in this compound? 1, 2, 3, 4, 5. So 6 minus 5 is positive 1. So because of the formal charges in the structure to the right, it is less favorable, and that means you choose the structure to the left as the preferable one. This is just showing the formula for formal charge. I don't know if you're going to relate to the formula better than my talking, but whatever one sinks in and you understand better, use. Just to summarize, the best Lewis structure is the one with the fewest and lowest formal charges. If you have a structure that has a charge, either overall negative or positive charge, make sure you put that negative charge on the most electronegative atom. So what are the relative electronegativities of nitrogen, carbon, and oxygen? Oxygen is the most electronegative, so the negative charge should go over it. If you draw out the Lewis structure for ozone, okay, 3 oxygens bonded together, and you follow those rules, you're going to end up with a structure like this, and the plus and minus are just the formal charges. It turns out, though, this is a correct Lewis structure. It turns out, though, that when scientists analyze the actual structure of ozone, they find, let me just redraw what we had on the other page. They find that the bonds between the oxygens are identical on both sides. They have the same strength, they have the same length, and the way we have this Lewis structure drawn implies that one of the oxygen-to-oxygen bonds should be shorter and stronger than the other one, and that's not the case. So scientists realized there was something not represented correctly in that Lewis structure for ozone. And the theory they came up with is something called resonance structure. So if there are two equivalent structures, you can see that these are equivalent. I've just swapped the double bond with the single bond, and they're equivalent. If there are equivalent resonance structures that can be drawn, then you draw them. And what you say is that the overall Lewis structure is a hybrid of these. So it's not that the double and single bonds literally switch places back and forth. It's that the truth lies somewhere in between those two structures. So really, in real life, what's going on is the double bond is partly located between two of the oxygens and partly located between the other two. So that is called delocalized electron. And these are called resonance structures. And finally, we are almost done. There are some exceptions to the octet rule. I said earlier that almost all atoms want 8 valence electrons, which is considered a full outer shell, which makes them similar to a noble gas and stable. There are some atoms that are stable with either fewer than 8 or more than 8. So let's talk about some of those. Some Lewis structures, for example, nitrogen monoxide, if you count valence electrons, you get an odd number, 11 electrons. No matter what you do, one of the two atoms involved are not going to have an octet. They're going to have an odd number. So the structure to the left, nitrogen has 2, 4, 6, 7 electrons around it, so it doesn't have an octet. Or if you draw it the other way to the right, oxygen doesn't have an octet. So there's nothing you can do about it, but nitrogen monoxide does exist. And so one of these two is not going to have an octet. One of these two is going to be deficient in electrons. So which one of these two structures, which one of these atoms, nitrogen or oxygen, do you think would prefer to be deficient in electrons? The one that is least electronegative, which would be nitrogen. So if one of them has to be deficient, pick the less electronegative one to be deficient, and that would be nitrogen. Boron is another exception. Boron is happy with 6 valence electrons around it instead of 8. Okay, just have to memorize that. If you were to draw, let's say, boron trifluoride, the Lewis structure, and if you tried to give one of the boron-fluorine bonds, turn it into a double bond so that boron would have an octet, you would find that by doing so, fluorine, the most electronegative atom ever, has to take on a formal charge of +1. That is not going to happen. So no matter how you draw it, one of the fluorines is going to have a formal charge of +1. No, no, no. Fluorine is way too electronegative to take on a positive charge ever. So that means that none of these structures will happen, and boron trifluoride exists simply as this structure. Okay, so boron only has 6 valence electrons, but that's the structure that it prefers to exist in. Again, that's just memorizing. Boron is a moron. That's how I remember it. There are also several atoms that can, we call it, expand their octet, which means they can hold more than 8 valence electrons. So I want you to understand which elements can do that. The elements that are on the third row of the periodic table, so here's the periodic table, here's hydrogen and helium, they're row 1. Here's row 2 with lithium, and then here's row 3 starting with sodium. So any elements in row 3 or below on the periodic table chart can expand their octet. So periods 3, 4, 5, and 6 can expand their octet or hold more than 8 electrons. Here is the highest level of a Lewis dot structure. This would be the level I would expect my AB students to be able to do. So let's say that I gave you the phosphate anion and I asked you to draw the Lewis structures. You should probably try to do that now if you have any idea what you're doing. If not, you can stick with me longer. So what you might initially come up with, if you follow the rules, is something shown here to the left. Then hopefully you would realize, okay, phosphorus can expand its octet, and whenever that is possible, when you have a central atom that can expand its octet, even though each atom involved may already have an octet, you want to go ahead and see that if by extending the octet, if you make the formal charges minimized. So the formal charge for each atom in the Lewis structure to the left here is shown, and you can see that every single atom has a formal charge. Not good. So this is a perfect example where you want to try to expand the octet and see if it minimizes formal charges. Remember how we do that. We take a non-bonding pair on one of the outside atoms and turn them into a multiple bond. So you can see here, we've done that. Now, recheck the formal charges. You can see by making this double bond, 2 of our atoms now have a formal charge of 0. And so, in fact, the Lewis structure to the right is the preferred structure because the minimization of formal charges. And that is it for the second lecture on bonding.